In today's video, we're going to be talking about resistors in parallel, and also the current division principle. They really go hand in hand, so it makes sense to put them into one video. In a very similar way to how we developed the resistors in series formula, we're going to begin by drawing a circuit, using Ohm's law and KCL, and determining what an equivalent resistance might look like to the voltage source that we're using. So, here is a voltage source, V. And here are two resistors, R1 and R2. V sends a current, I, and that current splits at this node here into I1 and I2. Now, one of the key parts of looking at a resistor series in, a resistor network in parallel is that they share a voltage, which means that the voltage across R1 and across R2 is both equal to V. That means that right now we can't necessarily solve for I, but we can solve for I1 and I2. I1 is V over R1. I2 is V over R2. Now, this is using Ohm's law. We can now use KCL, and we can solve for what I itself might be. I is going to equal to I1 plus I2. I1 and I2 are as shown above. And so if we were to add them together, we end up with V times 1 over R1 plus 1 over R2. Now, if you recall, Ohm's law says V equals IR, but we're really looking for this R, which we used to call R equivalent. And R equivalent is equal to V over I. So, if we rearrange this equation here for V over I, we end up with R equivalent, which in this case is given as 1 over R1 plus 1 over R2. Usually we write this more compactly as 1 over R1 plus 1 over R2 inverted to the power of -1. It's a little bit less straightforward than when dealing with series resistors, because then they just add it together. In this case, we have to divide, add the division, and then invert that whole thing. However, if you remember the formula, it becomes a lot easier. In general, if we have n resistors, some large number, the exact same thing happens. That circuit might look like this. And just for concreteness, I'm only going to draw a few resistors. I won't draw some unknown number. R1, R2, R3, and R4, and each of them has their own current. And this current here is the sum, I1 plus I2 plus I3 plus I4. So if we do the exact same analysis above, what we're going to find is that R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. In general, if I really do have n resistors, R equivalent is 1 over the sum from I equals 1 to n of 1 over Ri. This is our most general formula. Very frequently, though, we only really have two resistors. So, a shortcut that only works in two resistors, I'm going to put a little subscript 2 there, but I'll start dropping that eventually, is R1, R2 over R1 plus R2. Now, let's do a quick example. And I'm going to be drawing this in a way that might be strange to you. I'm only going to have resistors. I'll give them values, 1 ohm, 1 ohm, and 2 ohms. Now, you may have noticed that my derivation required a voltage source. In fact, what we can do is say if there were a voltage source across these terminals, we could do the derivation in the exact same way. So we're just going to ignore that and apply the formula that we have. So Req is 1 over 1 plus 1 over 1 plus 1 over 2, all inverted to the negative 1. When you solve this, we find that R equivalent is 1 over 2.5 ohms. The huge benefit of developing these formulas is that once you see that there are resistors in series or in parallel, you can just collapse them into an REQ, again, to make that analysis easier. Let's now look at the principle of current division, which really follows directly from what we've just done. If you remember voltage division, we had an incoming voltage, Vin, and we divided it according to the values of the resistors. We're going to do something extremely similar here. Now, it's important to notice that there are general formulas for this that work for any number of resistors. I'm not going to develop those general formulas here. If you're curious, you can look in the textbook or online. We're only going to be dealing with a network that has 2 resistors and a voltage source. Specifically, this is going to be Vn. This is R1 and R2, and this is I1 and I2, with the current I coming in. A typical question we might ask is, what is I1? I2. So, we begin by using Ohm's law, and we know that Vn is equal to I, R equivalent. So, I'm going to use that formula we developed above here for the 2 resistor case. Given this, I know then that V is equal to R2 R1 over R2 plus R1 multiplied by that current I. That's what Req is. Now, I don't actually need to solve for I. What I'm really looking for is what is I2. If we use KCL, what we have is that I2 is V over R2. But V is given by this. So let's substitute it in for V and see what we end up with. This is R2, R1, all over R2 plus R1 multiplied by that R2. And then all of that is multiplied by the incoming current I, which, like I said, for now I don't want to solve for. Well, those two R2s cancel, so what I end up with is R1 over R2 plus R1 times the incoming current I. And that is the current division principle. By a very similar argument, I1 is R2, over R2 plus R1 times I. Notice something very, very similar to the voltage division principle. We have a resistor divided by the sum of the resistors multiplied by an input. In this case, it's the current. In the previous case, it was the voltage. One major difference, and a brief blip that I made there, is that R2 is used to find I1. R1 is used to find I2. In the voltage division principle, R2 was used to find V2, and R1 was used to find V1. Now, the important thing about this is that I didn't really bother solving for I. I could have done so by finding the equivalent resistance. But here's an example where it actually is far easier to just use current division, and that's typically when you have an actual current source, or if you know I in the first place. So here's my current source, and we have our 2 resistors, and let's say this is 10 amps, and this one here is 100 ohms, and this one here is 50 ohms. Presuming that I'm interested in I2, I can now solve for I2 directly by just applying the formula rather than doing a complete analysis. I2 is 100, remember it's the opposite resistor, over the sum 100 plus 50, or 150, times the incoming current I, which is 10 amps. If you solve for this gives me 6.7 amps. And that's it. I didn't need to do the analysis of the circuit because I could use the formulas for current division. In the next few videos, we're going to be seeing how we can use these principles in order to solve circuits by combining resistors in series and in parallel in the same circuit.